this a little bit more in detail. Now, initially when I first started designing this, it was a theory, right? It was a theory I had, and I wanted to test the theory with a jig, which is what this thing is. It's a jig setup to test the theory. Well, it turns out that it's become fact. I'll explain why. It's really quite simple. Right, we have a coil. I'm going to draw a couple of coils actually. We have our coil, right? I'm just going to draw a spiral, right? So we'll connect this to the middle and this one over here, right? Rather than messing my drawing up, because I don't want to mess my drawing up too much, I'm going to just grab a magnet a minute. With a normal coil, you have a core material in the middle. Let's just put some lines through it. So what happens is with a normal magnet, with normal coil or magnet, you have a say a particular field, like say south, and that field enters the coil, and we've got the same field exiting the coil. Now, because of that, we have a lens effect, which is what we call drag, right? So we have drag, right? Well, because of this new device, the way it works, the core is actually moving, and it's not in the coil itself, it's moving. That's number one. That's the difference with this. And another difference is the fact that the pole reverses when it gets to the center of the coil because of the switching that's taking place. So let me just demonstrate with the magnet. So basically what's happening, because we've got two stationary magnets, one over here and one over here, it's simulating the effect that the magnet flips over halfway through. So as the coil enters, we have a lensing effect, but at the same time that this is entering, right, we have let me see, I'll just split this into two actually, that's the easiest way of doing it. If I can do this. Right, so I've got two magnets now. So one magnet is pulling, which is one pole, which is say south. The other magnet is pushing, which is say north, right? So you get two different lens effects. You have a positive lens and a negative lens effect. So what's happening now is we have the entry point of the coil, which is the coil that's wrapped on an entry point over here, and we have the exit point over here, which is the other end of the coil. It's the same coil, right? So the exit, we're going to put a big E here actually. Entry, oh god, I can't put E again, I'll have to put a big I for input or incoming. So that's going out and that's coming in. So that what we have now is two simultaneous magnets passing the inside of the coil and the outside of the coil at the same time. So we have different poles, right? We have the inside of the coil is seeing say north, and the exit side of the coil is seeing south. But because this is entering, right, and this one is actually exiting, what we actually do is create two different lens effects. We have a positive lens effect and a negative lens effect because of the different polarity. But we are generating power in the coil. But the two lens effects cancel themselves out, so it's like they're being basically totally wiped out. The only thing that we do see a little bit of drag is actually when the two poles cross over to that point where the exit coil or side sees just one pole and the entry point isn't actually seeing any incoming pole yet, because the rotors are sort of over here somewhere. So we have a bit of a gap. And it's this very slight imbalance which is causing a slight amount of drag, but not much. So we have the two fields are crossing the inside and the incoming and the exit side of the coil at the same time. So this is what we have. A conventional magnet, you just have one pole, you just have one magnet entering and one magnet leaving, and then you have drag. But because we have two opposing, and because that one's leaving the coil and this one's entering the coil, we still have an in-phase power generation of the coil. So what would happen actually if you induced a voltage in the coil to repel the magnets? Well, basically they wouldn't do anything, they wouldn't go anywhere, because they're actually being cancelled out. That's the whole point. They might move a little bit, but that's the differential, that's the problem that I have to overcome, that little differential that is like the slight imbalance. But there's, yeah, anyway, you get the idea. So obviously the coil is wound in I'll draw the coil so it's more properly represented, but it's basically wrapped. So I don't have to draw this in 3D, I'd have to, it's sort of like this, isn't it? It's, and it goes around like this, and right. So what's happening is when the laminations, the rotor passes the magnet pole that's over here, which might be, say, south, and there's another magnet over here which is the north. What's happening is, as the steel is actually, well, I'll just draw these lines, the steel is guiding the field out like this, and the south is entering, and at the same time we have the other laminations on this side, which are, I'm just going to draw some lines through the coil like this. So I'm really bad at drawing stuff, I really am. So the magnets themselves are, because they're stationary, they are creating our null point, which is right in the middle. So we have a dead spot right in the center of the coil, and we need that dead spot because we have to transition this rotor, which is moving, which is what these lines are. This rotor has to, when it enters the center point, transition from the south to the north. So we have this dead spot right in the middle, and then it crosses over into the north field. So it actually changes, it becomes bipolar. Effectively, it's a bipolar generator. Anyway, I wanted to explain it. You'll probably understand it a bit better now, maybe. Nearly chopped my fingers in these magnets as well. So obviously it's not conventional. Where's my other drawing gone? Oh, it's underneath here, isn't it? So as we saw, we got the north and then the south. Actually, it's probably easier down here, but so these basically transition polarity when they get to this center point and then become a different pole. So instead of having drag effect, we have a cancellation of that effect. So it actually adds to acceleration slightly, but in reality we don't actually see any change in the RPM much at all. There is an imbalance, though, as I said, because the distance between these here and the distance between here and here is different, so that's causing my imbalance. So I'd probably have to readjust that to sort that out. Now, I know it's not to scale, I know that this drawing's not to scale, but if I get my calipers and I measure the distance between basically there and there, we have 30 millimeters. Right, that's between these inner points. At the outer points we have a distance of what is it? This is not to scale, remember. We have a distance of about 70 millimeters, 69.72. Now if you go around to this gap, you'll see there's a discrepancy in the distance between these two. The distance between these two is 53, and the distance between yeah, it's 53 there. So that is the problem. That's the discrepancy in the balance. So what I can do, and it's probably a good thing to do actually, is to scale this drum to make a larger drum, but keep these laminations the same, right? So that what I can do is have a bigger gap between there and there, so this white space area would have a larger gap. So what I would need is, if I measure this, that's about 77 now, about 77. So what I would need is a space between these there and there of 77 millimeters. Well, this is obviously not scale, but the real thing would be different. So what I'd have to do is go into SketchUp, model it, build a scale slightly larger than this, using the same lamination arrays, but just have a bigger space between there and there, if you get what I'm saying. So that way I could equalize the do away with that slight discrepancy which is causing a small amount of drag. It would bring it all back into balance, because at the moment it's not in balance. Oh, I didn't actually show you the waveform, did I? I think I should show you that, and you'll see what I'm talking about. So I'm going to turn the oscilloscope on. Right, I'm just going to put the oscilloscope on. I'm going to put my camera in this stand. Oh, where can I put the stand? I think I can. Maybe I can stand it on my printer bed. I need to get these things off though, because right, one. Now come off, you buggers. 2, 3, 4. Don't break a nail. 5. Need to get the markers in the way. I'm going to need these as well at some point. I'll just stick them over here for now. Right, I'll stick this on my printer bed. It should give me a higher view. It's not heavy, this, so. Right, I'm just going to put this in here and hook the oscilloscope probe up, which is that one, I think. And I'll show you the waveform. Stick this back on voltage. Oh, by the way, the oscilloscope is set for ×10, but the probe is still going to be ×1. So any readings that you actually see on there, you have to divide by 0, because it's easier than messing about with my scope and turning it down to 0 ×1. Because you see, what I'm trying to do is I'm just trying to get a better waveform on it. So if it says it's obviously half a volt, so it's going to say that it's higher than that, but it isn't. Just so you know. Just a minute, where's my torch? I can't see the damn thing. Ah. Right. Oh, it's on ×10. I want to know ×1. Hang on a minute. Right. I don't want to short it out either. Right, so that's the waveform. You can see that discrepancy problem is due to that gap spacing, and that's why it keeps jumping on. It won't lock properly. So get my phone out of here again. Come out with your bugger. Right, so that's why the waveform is a bit distorted, where I've got high peaks and big peaks and little peaks, and the frequency is 337 Hertz. Obviously you have to divide the voltages by 10 because it's not 23, It's actually probably 2.3 actually, peak to peak. And yeah, so as you can see, it's a good sine wave. It's just that the waveforms are uneven because of that non-linear spacing on the rotor. And the only way I can bring that back into alignment is to get the spacing right. And but actually I might do something else to improve the output. Instead of just increasing the spacing and having a white dead spot, because if I increase the scale of this drum, make it bigger, I'd end up with a big dead spot in the rotor. All I need to do is, you know them other segments I've got, the other ones I made? Why not just have 6 segments instead of 3? Because having 6 segments, because obviously by scaling this larger, it means that it means I'm going to have more drag on the rotor because of the wind resistance, air resistance. So I'll have more drag, and I'll also lose power in the fact that my RPM would be slower. But I can gain that back. I can recover that lost potential output by adding the other segments into the dead spot, so that we have 6 segments instead of 3. And that would basically be like doubling my rotational speed. So it would be equivalent to, instead of having 3000 RPM, it would be like equivalent to 6000 RPM. Do you see what I'm getting at? Because we'd have more switching much faster. So that's what I'm thinking of doing actually, is scaling it so we can have 6 segments. And it would switch twice as fast. I guess if you see what I mean. Anyway, so that's what I'm thinking of doing at the moment. It means printing a whole new setup, which is, I'm not looking forward to doing that, but you see, the good thing about this, if I just do that, if I just add the extra segments, I can still use the same coils. You see, I can use the same coils, although the only problem was the diameter of the drum will be less. It will be less steep, as in the curvature will be more shallower. So I'm going to have some issues with the circumference. So obviously what I could do with that situation is remove the coils off there, basically break the legs off and remove the coils and just transplant them onto a new canopy with a wider circumference. So I can still use the coils, but I'd have to transplant the coils across to a new canopy. Well, I think I'm going to do that later, to be honest, because I've just made these 2 canopies. I've got one in there, and I've got another one there ready to wind. I've got this one ready to wind, and I don't want to chuck it in the bin. I've just made the damn thing. So I'm going to wind some more coils first. I'm going to continue testing with this one, but I'm just saying, at some point I can expand and scale this up. But I'm not going to do that just yet, because we still have more coils to wind on these things, and even though the circumference will be larger, because the coils can be removed from these by breaking the legs off. I could remove the coils, you see, these little legs that stick out. I could snap them off or whatever at a later point and just transplant the coils across to the new canopies, which will be scaled up. So yeah, that's basically the idea for the future. Anyway, enough of that. I think that's it. At least I sorry, I showed you the waveform finally. Right, thanks for watching.